Today's tutorial we will cover how to use Excel as a means to calculate uncertainty. So you're going to go ahead and open Excel. Alright, so once it's open, what we first need to do is we need to set up kind of a table of values. So what we're going to do is, we had 9 different trials in LabVIEW, so I'm going to kind of make a little table below trials. The next thing we need is to put in our length, LS, and that's in meters, our mass in kilograms. We need our LS, our mass, and then we need to calculate V0 in volts, and we're going to have to back calculate that using the strain. So the next column we need is strain, and that's just strain itself. Now we need the initial voltage, and we need the excitation voltage, and we need the gauge factor. So for this lab we use VEX as 5. We used gauge factor, which is 2.05. Now remember, VEX is voltage, so it's got units of volt. And then the last thing we need is VI. So this is the value that LabVIEW gave you for the initial voltage after you calibrated the strain in the settings window. And for me, I'm just going to use 1.5 millivolts. So that's 1.5 times 10 to the minus 3. And I'm going to have 9 different trials. And now I'm going to insert my lengths and my weights. So I'm going to insert the lengths at the same location first. And then I'm going to go to my next location that I used of the 3. Then I'm going to do my final location. And of course I'm doing this in meters. And then the mass I need is 0.5, then I did 0.7, then 1. And I repeated that for each location, so I'm just going to copy and paste it for all 3. Now, the next thing I need to insert is my strain values from LabVIEW. Alright, so now that I inserted all my strain values, so now I'm going to insert the formula for calculating V0 based on strain, VI, VEX, and gauge factor. The way I'm going to do that is, this is equal to, if you take equation 7 and solve for V0 in equation 7 of the lab, you get gauge factor, which is this value here, times VEX times the strain, all divided by 4, plus the initial voltage. Now, since these 3 values right here, we want to keep the same values. So if I drag this formula through, now if I drag this equation through to copy and paste the equation by using this little dot here. So if you click Excel and you do that, you see this little the box in the corner of the cell right here. You click and drag it, it'll drag the formula and apply it. And you notice that the values aren't correct. And the reason is, when you drag it down, it shifts the reference down. So when you drag it down, it shifts the reference to the next row because you're moving that cell in calculations. So what we need to do is we need to hold that cell. It means keep the cell constant so that when we drag the formula through, it doesn't change. But we want it to change for strain. So for VEX, we're going to put a $sign in front of the B and the 1. What the $sign does is it tells Excel that when you drag the formula, do not change the reference. Keep it that specific cell. If I remove the $sign in front of the 1, it means that you can change the row number, but you cannot change the column reference. And if I leave just the $sign in front of the 1 and remove it from the B, then it just means that keep that number row, but you can change the column. So the row number will not change, but the column can change. I'm going to put a $sign on both, just to be consistent and make sure it doesn't change it. Same thing with gauge factor. Now we want the strain to change. So when we drag the equation down, we want it to change the reference to the strain values to the right. But for VI, we don't want to change it, so I'm going to hold that as well. And you hit enter. And now you can drag it down, and you can see it did the calculations properly. And you can check it by clicking the cell and make sure that the reference is the proper one. So it referenced the proper strain and it referenced the proper top values. So now we can actually start and set up the uncertainty. So what we're going to need uncertainty of the base in meters, uncertainty of the height in meters, which is equal to the base. So I'm just going to say equals to this cell. We're going to need the uncertainty of the mass in kilograms, uncertainty of LS in meters. We're going to need uncertainty of gauge factor, and we're going to need uncertainty of the DAC or resolution, and that's in volts. So to calculate the uncertainty of the resolution, we also need to know some more properties about the DAC itself. So I'm going to put in the number of bits, which is 24, and the voltage range that we're using, or the range, is equal to our excitation voltage times the range that it specifies. So it's plus or minus 25 millivolts per volt, right? So it's 5 times 25 for the plus, then minus the excitation times 25 again. And then that's in millivolts. So now we have the range calculated, we have the bits there. So now we can calculate the uncertainty of the DAC for resolution. Now that is based on the resolution equation. So the resolution of the DAC in volts is the range times 10 to the minus 3 divided by 2 to the number of bits, which is 24, minus 1. Now the resolution, the uncertainty based on resolution, is equal to half of that. So the uncertainty of resolution over here is equal to the resolution divided by 2. Alright, so now we need to calculate the uncertainty for the rest of these values. We also need to know the uncertainty of UVI. So UVI, and that's in volts. And then we're going to need to calculate the certainty for all 9 of these values for V0. Right click and insert, shells to the right. And then I'm going to say U V0, and this is in volts. And now we need to calculate that. Now, you guys have to determine the uncertainty of the base, the height, the gauge factor, the UM, and the ULS. I need a row here so you can actually put the values there. I'm just going to put in random values for this for right now so you can see how to calculate it. But again, you guys need to figure this out on your own. And I'm also going to put how to calculate UVI, but it's going to be based off the random values from before. So I'm just going to say some random values. So I'm going to say the uncertainty of the base is 0.1, the height is 0.1, LS is 0.1, UM is 1 gram, and the gauge factor uncertainty is, let's say, 0.02. So now to calculate the UVI, remember that on the handout, the DAC had a couple of different uncertainties to it. And that was USE, but that's based on the actual values, and you have UZE, or zero error, and that's volts, and that's based on the range of the DAC itself. So the range is 250 millivolts, so times to the minus 1, 250 millivolts, times, it was 0.05%, so 0.05 divided by 100. So that's the uncertainty based on UE. Now the uncertainty based on USE depends on the value itself. So I'm going to go ahead and have to calculate UVI in volts, and that's going to be equal to I'm calculating UCVI in volts, and this is U naught for the DAC, and this is UCZE, and then I'm calculating a UCVI. I'm calculating the UVI in volts for the DAC, so UDVI in volts. So this is 0.2% of the actual reading of the initial voltage. So 0.2 divided by 100 times the voltage itself, and that's the uncertainty. Now the uncertainty of the DAC for the VI is equal to UEC SE, and now I need to get my overall UC of the initial voltage, which is VI. This is VI. So this is all calculations for VI itself. And that's equal to the square root of the first one squared plus the second one squared. And now the UDVI, or the overall uncertainty of VI from the DAC, is equal to the square root of U naught squared plus UC squared. And that's what you get for the uncertainty of it. So down here, I'm going to insert another column. And we're going to find UC SE V0 in volts. And then this is UC V0. And I'm going to add in one more column here. And then finally we get UDV0. And these are all in volts. So the first thing I'm going to do is this is equal to 0.2 divided by 100 times the actual value itself. And now we have 9 different values, so I gotta drag this formula through. And this is the uncertainty from UC SE, so the sensitivity error. Now UC V0 is equal to the square root times the UC ZE, which is a constant because the range is constant. So I need to hold that cell. So I put in the $sign. And then I add in the UC SE V0 to that and square it. And then I drag it through and get 9 values. And now I can finally calculate UDV0, which is the square root of the U0 squared plus the UCV0 squared. Now U0 is one constant value, so I'm going to put it so it holds the cell and keeps that value through all the formulas. And now I'm going to drag it through. And now I've calculated the UD, the uncertainty of the DAC, based on voltage for the V0 measurement. So now I need to calculate U as strain. And the way I'm going to do that is using the relative uncertainty analysis. And I'm just going to apply the equation that I did in the previous video, and that is equal to the strain value itself times square root of the uncertainty of V0 divided by the value of V0. Now I don't want to hold these cells because I want them to change because each value changes. To the second plus VI, the uncertainty of VI, divided by the value of VI. And I want to hold these cells because it's a constant value. To the second. And then the last one I need to add in is gauge factor. So the uncertainty of gauge factor divided by gauge factor value itself to the second, and then end my parentheses for the square root. And again, I need to hold this one as well because it's a single value. And then I drag the equation down to get all 9 calculations. Alright, so then you have E, or Young's modulus, in gigapascals. And then you have UE of Young's modulus in gigapascals. So my values for Young's modulus were, so now I'm going to calculate the uncertainty of Young's modulus using the equation I have in the uncertainty analysis tutorial. and that is the value of Young's modulus times the square root of the uncertainty of the base divided by the value of the base. So you actually need to put the value of the base in here. And for me, the value of the base in meters was 25 millimeters, which is 0.025. And the value for height, h, in meters was 0.01, 10 millimeters. And then what we're going to do now is actually type in the equation, which is the value of Young's modulus times the square root. Then we're going to do the uncertainty of the base divided by the value of the base. Now this is a single value, so I got to put in the dollar signs. Now I'm going to do the height, and I'm just going to copy this part of the equation and paste it. And then what I'm going to do is I'm going to change the reference. So I'm going to say the height is what I want, and the height that I want here is D2. And I want F2, and here I want F1. And remember, for the height, it's the uncertainty of the height times 2 divided by the height value itself. And now we're going to be doing the uncertainty of the mass, LS, and then finally strain. So for the uncertainty of the mass, it's the uncertainty of the mass, and we got to keep that value constant because that value is constant. But the weight that we use for each of the 9 is not constant. So it's H1 divided by the value of our mass squared plus the uncertainty of LS, which is H2. Hold that cell as well. Divided by LS itself squared, and then the final one is strain. Now the uncertainty of strain is this value here, and this value of strain itself is this value here for this specific measurement. And then I square it, and then I finish my square root, and I hit enter, and then I can drag it through, and I get my uncertainty of Young's modulus. Now keep in mind that these values that I inserted are pretty high uncertainty values, so that's why it's such a high uncertainty for Young's modulus. If I change the mass to 0.5, I change the LS to 0.01, base to 0.01, and height to 0.01, you notice that the values decrease significantly. Now, keep in mind that this uncertainty in the mass is also very high because I'm saying it's a half a kilogram. In reality, it's probably more on the order of 1 gram uncertainty, which is basically 1 divided by 1,000. And then you notice that the order of magnitude of the strain of the uncertainty goes down even more. So this is how you apply the equations of uncertainty. Again, these uncertainty values are not correct uncertainty values. You need to find these on your own, and that's how you use Excel as a means to find uncertainty for labs that you have. So in the next tutorial I'll be using MathCAD, and then the final tutorial I'll be using MATLAB, and this is just to show you the software and how to use it for doing uncertainty analysis.